Let's start.
Is the recording is on?
Да.
Okay. Good evening. Do you see my whiteboard?
Да.
Oh, great. Unfortunately, my wonderful slides don't work, but so I will write on the whiteboard. Today, I will speak about the values of the SL2 weight system on a family of graphs that are not intersection graphs. Maybe the topic is just not the same that was in the annotation, but it is so. Okay. Well, do I have to remind about Hopf algebra of graphs and the Hopf algebra of chord diagrams?
Just few words.
Just how I want.
Чуть-чуть, немножко, в двух словах.
Okay. We have graphs. These are simple graphs. So we have no loops and no double edges or no multiple edges. We may multiply them. The product of two graphs, it's just their disjoint union. We may consider formal linear combination. Like this. Well, and we have multiplication, we have formal linear combination, and we have co-multiplication. It's take. It's the sum overall subsets of the vertex set of a graph. And is it clear?
No.
Okay, maybe some annotation is not so clear. There it's not obvious, but we have with this operation and we have some more operations, but I will not remind what is a Hopf algebra, okay? We have also chord diagrams. The multiplication of chord diagrams is like this. We have two chord diagrams. Oh, we delete and we так нет, давайте что sorry. We want to multiply two chord diagrams and we obtain a new diagram as follows. We delete a part of circle. This operation depends on the on the place or where we make this, where on the place where we cut. Well, maybe in this example it doesn't, but it depends. But we consider chord diagrams up to the four-term relation, which is which looks as follows. Так. Сейчас, чтобы... Так. We have... Так, давайте я вам лучше его покажу, чтобы не рисовать. Нет, окей. Так, сейчас. Yes, this operation is not well defined, but modulo the four-term relation, it is well defined. And the four-term relation is we have chords. You see only the blackboard, isn't it?
Да, видно все.
So we take two chords. And such an element equals 0. This is a four-term element. And we take all the... And here there maybe here are some other chords, but they are all the same for all the four diagrams. Like this. And so modulo this relation, the multiplication is well defined. So we also consider formal linear combinations of chord diagrams and co-multiplication. The co-multiplication, the formula is the same, but we consider here V of C is the set of all chords of a chord diagram, and so if we have this is V of C, and for example here is this restriction is it's V1. It's V1. It's just this chord diagram, for example. So this is a co-multiplication. The example of the restriction is here. Chord diagrams modulo the four-term relation also form a Hopf algebra. Well, now I will speak about the map from chord diagrams to graphs. It's a very important definition in today's talk. Intersection graph. To each chord diagram, we may assign its intersection graph. To each chord, for each chord we have a vertex, and if chords intersect, that means that then corresponding edges connect with the edge. And if the chords do not intersect, then we have no edge.
Полина,
Да.
там в первой строчке, наверное, правильно нет. Во второй с конца. Там одну из вершин сделать синенькой в правом крыле.
Wait, да. Thank you, yes. We have two chords, and this is an edge between two chords. Да, спасибо. Thank you.
Не настолько синий.
Well, for example, if we have such a graph, wait, sorry. I should start. Of course, I should start with a chord diagram. Sorry. We have some chord diagram. And we so the intersection graph is like follows. These vertices are connected with an edge. These are not, because the corresponding chords do not intersect. And all these chords intersect, so we have edges here. But it's important that take first the different chord diagrams may have one intersection graph. And there are graphs such that are not intersection graph of any chord diagrams. Okay, here C are chord diagrams. C, C1, C2, and C are chord diagrams, and G are graphs. G is a graph. For example, I think it's an exercise to invent two chord diagrams with two different chord diagrams with one intersection graph. But here is our main example of a graph that is not an intersection graph. This is not an intersection graph. And here there are some other examples. For example, this is this graph is not an intersection graph of any chord diagram. And if we take a wheel with wheel on 8 vertices, this graph here, I hope this is also not an intersection graph of any chord diagram, but this example is most interesting for us today. May I clear these drawings?
Да.
Okay, because there is a recording, so today we are interested in the graphs of a particular form in joins of an arbitrary graph J, and G, sorry, J, and a discrete graph of n vertices. Take some graph G, and arbitrary, and take a discrete graph on n vertices. Too many vertices, it will be hard. And the join of these two graphs is a graph that contains all these graphs, or two graphs as subgraphs, and it contains all the edges between all the vertices of these two graphs. So we take all the vertices and like this. For example, a complete bipartite graph is also a graph of this form. I will denote these graphs as like this. Gn. And I will consider, I think, only the graphs of such a form. And note that if we take a cycle on 5 vertices, I will denote it by C5, then a graph of such a form is our graph considered with graphs that are not intersection graphs.
For n equal to 1.
Excuse me?
For n equal to 1.
Yes. Oh, sorry. Yes. N equals 1. Yes. Thank you. But if we have n here and n is greater than 1, then this graph is not an intersection graph.
Если граф содержит один подграф, который не является графом пересечения, он же никак не может быть графом пересечения.
Значит, подграфы я бы...
Shouldn't it be a strict inequality?
No, it's not a strict inequality, because if n equals 1, It's also not an intersection graph.
Ah, okay, thanks.
Yes, we have. If we want to have strict inequality, we m greater than 0. Well, okay. The graph of such a form. I will clear all drawings. The graph of such a form. No. If we have a graph Gn, then any subgraph of Gn is of the form H is a subgraph of G, and K is less than or equal to N. So the graphs of the form G, N sorry, no. The graph of the form Hn, where H is a subgraph of G and N is equal 1, 2, and so on. They generate a Hopf algebra, Hopf's algebra in I didn't made this notation, but we denote by G the Hopf algebra of graphs.
Тут следует сказать, что такое подграф. Мы, говоря подграф, мы всегда имеем в виду индуцированный подграф. То есть мы берем какое-то подмножество вершин в нашем графе, и все ребра, которые из нашего графа, которые соединяют эти вершины между собой. Вот это подграф, это то, что называется индуцированный подграф.
Okay, thanks. So we consider induced subgraphs. We take a subset of the set of the vertices of our graph, and we take a graph which have with vertex set v1, and the edge set consists of only of the edges such that they connect. Okay, just of this subset V and U are in. Yes, we have a subset of vertices in the set of vertices of the graph G, and we have a graph with vertex set V1, and the edge set consists of all the edges which connect vertices of V1. Should I provide an example of AG?
No need, I believe.
Okay. Okay. Once I will clear my drawings. And now I will speak about primitive elements. It's important. Yes, I will know that if we have a chain, if of graphs, if we have, then we have a nested subalgebras. Of this subalgebra of this Hopf subalgebra, so Hopf subalgebras of the Hopf algebra of graphs. Okay, now I will speak about primitive elements. The element of Hopf algebra is primitive if, I think I should, it's a definition, so this is true. Primitive elements are very important for us because there is a Milnor-Moore theorem which states that they and their combinations, they generate all the algebra. They generate. Так, сейчас. It's true for. Yes, maybe it's true not for any Hopf algebra, but in our case, this is true. And that is important for us, that there is a formula for the projection. The primitive elements form a space, linear vector subspace. And if we consider Hopf algebra of graphs or the Hopf algebra of chord diagrams, then we have a formula for projection of any element to the subspace of primitive elements. Like this. We have G minus we consider all the decomposition of the vertex set of G into the disjoint union of two sets. And then we consider Что? Non-empty. Yes, it's they are non-empty. It's crucial. Here we have factorial. V2, so we have -1 power k minus 1, k minus 1 factorial, and the sum over all the decomposition into k non-empty sets and the product or disjoint union of the restrictions of the graph onto this subsets.
Там объединение несвязанное должно быть VG.
Сейчас.
В нижней строчке, где суммирование идет по разложению.
Yes, thanks, yes. Here we have VG.
И там еще дальше многоточие. Да, нужно сказать, что это, значит, проекции из пространства на подпространство бывает много. И это одна выделенная проекция. Это проекция, такая ядро, которое это разложимые элементы. Это очень специальная проекция.
Yes. Do you see the screen? You see only the white screen, yes? This is a projection along the subspace of decomposable elements. Element is decomposable if this is a project of two other elements, and here it's a projection along this subspace. Because there are some other projections, but they are not all so interesting. Okay. And we have some. I will clear all drawings. We may construct generating functions for the graphs and for the projections of graphs, because we have graphs of this form. So we may take G, which equals G and 0, G join 0, G join 1, G join 2, and so on. And we may also consider the projections. And so on. And we may construct generating functions. Of T of S. G. These are exponential generating functions. Sorry, it's N K plus V of G, of course.
Значит, Полин, полезно написать индекс G у каждой из этих функций.
Yeah. Спасибо.
И хотелось бы обратить внимание слушателей на то, что Ну, обычно производящие функции – это функции с числовыми коэффициентами. А здесь коэффициентами являются графы.
Yes, here we take just graphs.
Графы, ну, или линейные, или даже линейные комбинации графов. То есть мы имеем дело с производящими функциями, коэффициенты которых это элементы нашего АЖ.
Thanks. Yes, here each generating function depends on G and on S, and know that here G and G join K, it's not a number, but it's a graph. Oof, a graph. Well, and for generate, it's not that easy to write such a generating function for projection, but for graphs of such a form, where there is a nice formula. I will try to show this formula, but sorry, I will show it in the text because there is some problem with the slides. Take okay. Okay, sorry for this delay, but but this is I like this. I like this formula, and I want to show it.
Excuse me, what is this variable S?
Excuse me?
Что такое переменная S?
S is just a formal variable, which in a generating function we always use a formal variable, and here it's S.
Thanks. A formal variable, okay.
Yes, it's a formal, yes.
If we have some sequence, A0, A1, A2, and so on, then we can construct an exponential generating function for this sequence, which looks like A0 plus A1 times S1 plus A2 times A0 plus A1 times S plus A2 times S squared over 2 factorial plus A3 times S cubed over 3 factorial and so on. So it's just a formal function whose coefficients are elements of our sequence. And here the sequence is a sequence of graphs GK or its linear combinations, P of GK.
Thank you.
Okay, I think I will just write it. It's not so long. If we have a generating function S, and we take it's too the font size is too big. Here it's the sum like in the projection formula. But instead of the graphs, we have generating functions, but these are generating functions for graphs. It's okay. I think it's not obvious that this letter is G. this is G, and here it's the same G. G restrict to V1, G of G restrict to V2, and so on. G of G restrict to VK. And then we should multiply this all to I will explain what is it. If X this is a very simple thing. This is just a graph, or it's just one vertex. Sorry?
The letter is S or X?
Oh, sorry. The letter is yes. Yes.
Давайте прежде чем объяснять, что это такое, давайте сделаем, во-первых, напишите слово теорема, поскольку это ваша теорема, вам тут есть чем гордиться. Вот, хорошо, да. Во-вторых, давайте сделаем, чтобы было чем гордиться, давайте сделаем утверждение. Во-первых, перед знаком суммы нужно поставить сумму по k.
Yes.
Ну там, я не знаю, до бесконечности.
Yes.
Можно от k до количества вершин. Дальше, да. Дальше, во второй сумме, там не получается стереть. Да?
Окей, пусть так будет n, yes.
Во второй сумме у вас суммирование ведется по всем разложениям множества вершин графа G. А то у вас пропало, что это не связанное объединение равно V от G. Да. Там G не нужно, слева от знака равенства G не нужно. Вот так. Вот теперь уже хорошая формула, и можно объяснять, что такое K1,0.
Это просто относится к алгебре Хопфа графов, и тут пока никаких инвариантов еще ничего нет. Да?
Нет, это чистая алгебра Хопфа графов. Да. Ну, да, это алгебра Хопфа графов, ничего. Это даже не алгебра Хопфа хордовых диаграмм, потому что в хордовых диаграммах нет таких подалгебр Хопфа. Ну, то есть есть, но мало.
Ну, да. Oh, yes, here, thank you. Yes, here we have disjoint union. We take vertices of G and we take all the disjoint unions of subsets, like it was in the projection of the graph. Here are the same coefficients. Here we take all restrictions, and here it's an exponential generating function, and this is just a graph which is one vertex. It's this notation means that it's a complete bipartite graphs with one vertex.
Давайте все-таки формула еще неправильная. Значит, первая сумма должна быть от k равного единице, а не от k равного нулю, потому что от k равного единице и минус единица должна быть в степени k минус 1.
На самом деле у меня тут поэтому так и было написано внизу, что по всем корректным разбиениям. Типа some overall well-defined partitions.
Ну, это трудно понимать. Это минус единица в степени k минус 1.
Oh, sorry, it's very important. Yes, it's very important. It's power k minus 1.
Это, вся эта вместе сумма, она конечная получается.
Yes, it's finite. Да, она конечная.
It's finite, but the generating series, they are not finite.
Ну да, там вот экспонент уже содержит бесконечное число слагаемых.
Да.
And it's easier to work with this formula because if we know generating functions for a graph and for its subgraph, we may write the generating function for the projection of this graph. It's easier than try to find out from the formula, the general formula. Okay.
В этом произведении экспоненты возводятся в степень k.
Да, К.
А это означает, что это k одинаковых сомножителей, а слева стоит тоже k сомножителей. Соответственно, нужно эту экспоненту можно к каждому сомножителю приписать, правильно? Это какой смысл имеет?
Да.
В этом есть какой смысл?
Вообще, может, да. Я, честно говоря, я не помню. Может быть.
Можно.
Да. Да.
Мне кажется, оно так и получалось.
Ну, действительно, это хорошее соображение, что, может быть, правильная производящая функция – это не g с индексом g, а g с индексом g, умноженное на экспоненту от минус k1 0s. И тогда… Может быть так, но в любом случае эта формула работает, да.
Okay. Yes, it works.
Сейчас, а это разве не одно и то же?
Что?
Это же и получится. Нет?
Что именно?
Что если взять граф G, просто граф G умножить на экспоненту на экспоненту, то не получится производящая функция G красивая от x. Мы же берем граф G сам граф без…
Нет.
А вот в этом произведении какие стоят G?
Под графов.
Нет, G красивые стоят?
Да, вот эти G красивые, да.
Ага, понятно.
Нет.
Это не сами графы, да, это и производящие функции.
Мы уже красиво добавляем джойны, а в этой экспоненте мы добавляем, наоборот, несвязанные суммы. Понятно.
Вот.
Добавляем джойна, а вычитаем без джойна. Понятно.
Окей. Ну, так вот. No, I will not prove it because I do not have time. Okay. I will speak about the weight system via sl2. Okay. Так. I will clear all drawings.
Yeah.
And now I will speak about the weight system. Should I give the definition?
Yeah.
Okay. We have let G be a Lie algebra. With a non-degenerate invariant form. We can this form, it's like a bracket. We have an orthonormal basis.
Напишите, что это невыраженное.
Uh-huh.
Invariant. Generate invariant.
X is some orthonormal basis. And then let C be a chord diagram. And the A of C, let the A of C be its arc representation. And I will give an example immediately. We have such a chord diagram. Something easy. We cut diagram somewhere, and we obtain 3 arcs, and but chords intersect, so the arcs also intersect. Okay, this is an arc representation of the chord diagram, and for any arc we write elements of our basis. Basis is x1, x2, x3, and so on. X. Oh, okay. xa1, x. Oh, I will do it like this. We may use the same elements for different chords, but the elements for each chord, this is the same element. And then we take all such products.
Полина, мне все-таки кажется, что проще использовать индексы И, Ж, К.
Yes. Oh, yes, because A is an arc representation. Yes. Okay, sorry. It's not A, but it's I. xa1, xa3, xa2. And here we also have xi1, xi3, xi2, xi1, xi3, xi2. And the sequence depends on the arc diagram. And this is the sum over all arc representations. And we obtain a function on chord diagrams. And this result, I recall that we consider chord diagrams up to 4-term relation, and In this case, the result of this operation is in the center of universal invariant algebra of our Lie algebra. And
Полин,
да,
странно написано. Это не сумма по всем видовым представлениям, а сумма по всем индексам.
сейчас.
По всем
Что-то мне тоже не нравится.
От единицы до размерности алгебры.
Угу. Так, вы считаете. И один. Yes. Yes. M is G is it's a finite dimensional algebra and its dimension equals M, and here we have such a sum. This is a V. Sorry, да, я неправильно написала, sorry. So the Wx of A. Wx of A. We have some properties. Wx of A is in the center of universal invariant algebra of our Lie algebra. This operation does not depend on the choice of A. It also does not depend on the choice of the orthonormal basis. And on it and this map satisfies the four-term relation. So we have a homomorphism from a homomorphism of commutative algebras because we considered chord diagrams up to four-term relation. Yes, so it's a map. It does not depend on A and on X, so we may write like this. And diagrams. Two polynomials. Okay, to the center, actually to the center, because we don't know that yet that the center polynomials, but it's a common case.
А нарисуйте там стрелочку, чтобы а то у вас минус стоит.
Ой, да, sorry. So we have such a map from arbitrarily algebra of finite dimension.
Ну, значит, всякая алгебра Lie с невырожденным инвариантным скалярным произведением мы сопоставляем весовую систему, то есть функцию на хордовых диаграммах, удовлетворяющую 4 членных соотношения. И это весовая система принимает значение в центре универсальной обертывающей алгебры Ли. Это звучит страшно, но в том случае, который мы будем рассматривать, в случае алгебры Ли sl2, этот центр представляет собой просто кольцо многочленов от одной переменной, а уж представить себе кольцо весовую систему со значением кольца многочленов не так страшно, как со значениями в центре универсальной обертывающей
алгебры. Yes, and yes. Oi, thank you. In this case, this is in this case the center is take of is generated by the Casimir element, so it's just polynomials in C. C equals. Should I give the definition of sl2? Excuse me?
Не надо. Это x, y, z не обязательно. И есть, значит, какой-то для любого ортонормированного пояса x, y, z, ну, нужно сказать еще какое там скалярное произведение, но не обязательно. Важно, что для любого ортонормированного пояса, вот элемент x квадрат плюс y квадрат, для любого ортонормированного пояса x, y, z, элемент x квадрат плюс y квадрат плюс z квадрат порождает центр универсальной обертывающей алгебры. И, соответственно, этот центр – это не что иное, как кольцо многочленов от этого элемента.
In particular, yes, thanks. And in particular, if we take a diagram with first, if we take an empty diagram, then it's just one. If we take a diagram with one chord, then the value equals C, and it's easy to check. We just write here XX or YY or ZZ and take the sum. Now we have Chmutov-Values relations. The first relation, I'm sure I can draw it. I'm sure. If we have a leaf in our chord diagram, then that is a chord which intersects only one other chord. Then we may delete it and multiply the result to C minus 1. Here, by a diagram, we assume the value of our weight system on it. We have some other relations by Chmutov and Values, and I think I will show it because it will be, I think it will be faster. Чтобы другое окно показать, надо остановить демонстрацию и другую, да?
Да.
Sorry. Sorry, I have, because I said that my my slides are off. So these are Chmutov-Values relations. In fact, there are four relations, or with four six-term relations. But if we have a chord diagram without leaves, then they have three leaves that are arranged like this or like this. So we may use one of these relations, but moreover, is if one of these diagrams is a leaf, we also may use these relations.
Excuse me, could you zoom in the images you're showing?
Zoom in?
Увеличить, да.
Yes, like try to see.
Вон плюсик в кружочке.
Плюсик.
Увеличить изображение.
Правее, правее.
Я поняла. Сейчас. Сейчас, извините. Zoom. Так.
Либо плюсик, либо процент.
По центру прямо на почему-то.
Не, мышка не работает. Мышка убегает.
Сейчас maybe. Maybe I may zoom here. Так, wait.
Просто внутри Acrobat Reader.
What? Yes, I want to do it inside the Acrobat Reader, but there are some problems. It's better.
No, in the yeah, that one.
Great.
Thank you.
Sorry. Yes. And these six-term relations, or there are.
Yeah, these six-term relations have the following form. They take a diagram and replace it by a linear combination of simpler diagrams. In the first three diagrams,
Sorry.
in the first three diagrams on the right, there is the same number of chords, but fewer chord intersections. Так или нет? Нет. In the last three, I see. In the last three diagrams, to the right of the equality sign, there is the same number of chords, but fewer intersection of chords. And in the first two diagrams, there are fewer chords than in the diagram on the left. That is why these relations can be used to compute the value of the WSL2 weight system recursively. Значит, соотношение Чмутова-Варченко – это рекуррентное соотношение на значение весовой системы sl2. Мы заменяем хордовую диаграмму линейной комбинацией 5 других хордовых диаграмм, что, конечно, сразу усложняет жизнь. Но зато все эти 5 диаграмм проще, чем исходная диаграмма. В последних 3 диаграммах столько же хорд, но меньше пересечений. Их пересечения от первых 2 диаграмм даже меньше хорд. And also all these diagrams, all 6 diagrams in each row, they contain the same set of additional chords that are not shown in the picture. The additional chords whose ends belong to dotted arcs of the circle.
Yes, the additional chords are all the same. Thanks. And there is a corollary also by Chmutov and Varchenko. This is easier to use because it's okay. It's easier. It's just easier to use. We have a chord. I don't like this color. We have a chord diagram. We have 2 chords arranged like this or like this, and we have a third chord, and we want to delete it. And so we have another 3 diagrams. We have a diagram with this chord just deleted. Oh, sorry. We have a chord. We have a diagram with chord arranged like this, And we have a diagram where we switch these chords like this. For example, if these chords do not intersect, we have these three diagrams. And if they do intersect, we have these three diagrams. And there is a theorem of Chmutov and Varchenko that there is a relation. Yes, and then in some cases it's easier to use this relation, and in some cases it's easier to use the six-term relations. Now I think I will speak about the results or about the process.
No, we are almost out of time. So please speak about the results, and you will discuss approaches to the proof next time, and maybe you will have your slides then.
Окей. Так, а результат лучше в виде, то есть теорему или сами вычислений, ну, то есть частных случаев.
Может быть, лучше частные случаи показать.
Окей. I will show some cases. Так. It is possible to, using this relation, it turned out to be possible to find out the values of the sl2 weight system on all graphs of this form when with the number of vertices less than or equal to 4. N is arbitrary, and so the result was in form of a generating function for the values, and we also have some results for the graph of the form C5N. Oh, sorry, C5 cycle on 5 vertices. For example, like this. These here are some. We have a result in the form of a generating function, but here are some values of VSL2 for different n. So in here, this is n. This is values on the graphs C5n, and here are values for its projection C5 and n. Know that this result, E.Krasil'nikov have some results for n, I think 1, 2, 3, and 4. I'm not sure about 4. 1, 2, and 3, and of course they coincide. And then it's also very important. Wait, what is it? And it's also very important that here these polynomials are of degree here less than or equal to n. Так, сейчас я хочу убрать эту штуку отсюда. Oh, great. Let's here we have polynomials of degree n plus 5. And here now we have polynomials of degree n plus 5 less than or equal to n plus 5.
Чего? Там разве степень не больше 5 должна?
Ой, sorry, да, извините, это же ерунда. Yes, it's we have a polynomial. We have a graph of this form. And here we have 5 vertices, and here we have a discrete graph on n vertices. But n may be very just and here the degree of the polynomial is less than or equal to 5. It doesn't depend on n. Yes, it doesn't depend on n, and that means that its degree is less than or equal to the number of, or it's less than or equal to the circumference of the graph.
Хорошо, давайте еще я скажу, про что еще будет Полина в следующий раз говорить, я надеюсь. Она сегодня не упомянула результат С.V.Chmutova, который состоит в том, что значение весовой системы sl2 на хордовой диаграмме определяется ее графом пересечений. Если две разные хордовые диаграммы имеют изоморфные графы пересечений, то значение этих хордовых диаграмм, то значение весовой системы sl2 на этих диаграммах совпадает. Поэтому мы получаем частично определенный инвариант графов. Мы знаем, чему равно значение весовой системы sl2 на любом графе пересечений. Вот графы C5n, начиная с n равно единице, не являются графами пересечений, поэтому мы вообще не знаем, есть ли разумная, может ли весовая система sl2 иметь разумное продолжение на все графы. В следующий раз Полина тоже скажет, что такое разумное. Однако ее теорема говорит, что если такое продолжение существует, то значения этой весовой системы на графах C5n должны быть именно такими, как у нее получается. Вот. И, значит, цель всей этой деятельности состоит в том, чтобы попытаться придумать, как определять весовую систему sl2 сразу по графу. Как, глядя на граф, понять, чему равно на нем значение этой весовой системы. Пока это очень тяжело, даже для графов пересечений, потому что соотношения Чмутова-Варченко, хотя и позволяют вычислять значение весовой системы sl2, но они имеют экспоненциальную сложность. На каждом шаге количество графов, количество диаграмм, для которых надо считать, увеличивается в 5 раз. Потому что они шестичленные, слева стоит одна диаграмма, а справа она заменяется на 5. Поэтому уже там для диаграмм, скажем, с 20 хордами мы в реальности вычислять значение весовой системы sl2 не умеем. И поэтому вот всякие такого рода производящие функции, которые дают эффективный способ вычисления, они чрезвычайно важны и могут подсказать, как можно считать sl2 для произвольного графа. Вы можете сказать все то же самое по-английски. И на этом закончим.
Okay, there is a very important statement of Sergei Konstantinovich Lando and S.V.Chmutov, which states that the the value of the SL2 weight system depends only on the intersection graph. So we may try to define, we want to define an invariant of graphs that which equals VSL2 for intersection graphs. And so we should know its values on, but also on non-intersection graphs. So if we have such an invariant, if there is such an invariant, an extension of the VSL2 weight system to graphs, then its values on the graph of such a form are given. Moreover, it's the Chmutov correlations are hard to use because we have 5 terms, so it's have an exponential complexity. We have 5 power n. So it's impossible to use them if we want to find the value of our weight system on a chord diagram with, for example, 20 chords. It's impossible. So it's nice then that we have some generating functions in some cases. Well, I think next time I will. Oh yes, next time I will repeat why it's important for us, and I will say some words about proof of this theorem, about the proof of the theorem that states that the values for these graphs are like this. Thank you.
Thank you. Are there any questions? No, thanks. See everybody next week.
Thank you.